that name.
Okay, welcome back, and we'll continue our lecture on gravitation. And again, this is a very, very dense, heavy, profound topic. And we talked about why people got confused about gravitation in the beginning, why they thought heavy things experienced. They basically fell faster all the time and stuff like that, but we've shown that really this is just because of atmospheric interactions, aerodynamic interactions, and so Galileo then shows in his experiments that that really the speed of falling is very much independent of the mass of the object, and then finally Newton comes along, and we've talked about this already, that what Newton really does when he discovers gravity, quote unquote, Newton discovers gravity. What's really happening is that he is determining the form of the equation of gravitation. And this is what I mean. This is what Newton discovered. And it had very, very profound implications. If you have two objects, M1, M is the mass, and M2, each one is going to experience a force due to gravity. Now, this, when we're talking about this example, we're in outer space now. We're away from any gravitational fields, be it the field of the Earth, the Moon, or any other object. We're somewhere where there's no gravity, some fictitious place. And so M1 experiences a force due to gravity in this direction, and M2 experiences an equal and opposite force due to gravity in that direction. And we'll call this Fg1 and Fg2. And they're the same force in the sense that they're the same magnitude, right? You know what I mean? Same magnitude, opposite directions. Now, so keep this timer up there. The equation that determines the size of that force, and please write this in your notes, okay, is the force due to gravity equals G, which is a constant that never changes, we think, times M1 times M2 divided by the distance between the two objects squared. Okay? That is the force due to gravity. And so this is what Newton discovered. He discovered that if you put the numbers into this equation, you'll get the correct force for gravity. Now, a couple important things. First of all, what is the denominator of the equation? Nicholas.
D squared.
Right, D squared. Excellent, excellent. Yeah, the denominator is D squared. So that means let's do a little bit of math here. Let's draw the distance now. Let's say the distance between here and here is 1 meter. And let's say that, just for example, G doesn't equal 1. Just pretend it does for right now. Say G equals 1, M1 equals 1 kilogram, M2 equals 1 kilogram. So they're the same mass in this case. So basically, the force due to gravity is going to equal 1 times 1 divided by 1. Andre, what's the force due to gravity?
Is it 1?
It's 1. Right. Excellent. And what's the units? of force? Right. 1 Newton of gravity. Okay, good. Now, let's say the objects are 2 meters apart. Okay. Now, remember, it's d squared, so 2 squared is what? 2 squared is what? 4. So now it's 1 over 4. It's 1/4 of the original force, but we only doubled the distance. Okay? So if you graph this out, this is what you get. Let's do a graph now of this gravitation equation. All right. So I'll use my nifty little thing here. Okay, one. There's another one. Okay. So on this axis we'll have distance x in meters. On this axis we will have force, and that's obviously in newtons. And we'll plot the 2 points that we just made. There's 1, 2, 3, 4, 5, 6, 7, 8, 10. So obviously if how do we do this? Those are meters apart. The further apart they are, the more the force will drop. So let's say this is 1 meter or 1 Newton and, wait a minute, sorry, a little confusing, forgive me. 1 Newton and 1/4 of a Newton, right there, something like that. I don't know, this isn't coming out very accurately. This would obviously be a half, this would be 1/4 down here. So, Andre, what was the force at 1 meter?
1 Newton.
Right, 1 Newton. What was the force at a half a meter? Or at 2 meters, sorry.
That was 1/4 Newton.
Right, 1/4 of a Newton. So this if you keep doing this, you have what's called an exponential graph. It looks like this. Okay. So the further away the two objects are, the graph falls off as the square of the distance. The closer the objects are, the more intense the gravitational force. Okay, now let's talk about the implications of what Newton discovered. First of all, there's one, so this applies to objects falling on Earth, such as apples, baseballs, or anything that decides to fall. But it also applies to objects outside of the Earth. And this is the big deal at Newton's time. Let's just go like this. Get a new page, right? New page. How do we get a new page? Does anybody know? Insert blank page. There we go. Okay. All right. So the big deal at Newton's time was showing that this equation applied to things outside of the Earth. And does anybody know what object he showed that the law of gravity worked for first? Andre?
Is it an apple?
No, that's on the Earth. An apple is on the Earth. It's something that's outside of the Earth that we observe, which is
Oh, asteroid.
no, close, but no cigar. Moon. Yes, the moon. The moon. So Newton looked at yonder shining sphere. Okay, and he showed that using his equation of gravity, so here's the Earth, Here's Earth. Here's Moon. Newton showed, I don't know, that didn't come out right. Hold on a second. Newton showed that his equation of gravity predicted the orbit of the moon. But now, you say, Newton showed that two objects that have mass are attracted to each other. How could his equation of gravity possibly have determined the period of the orbit of the moon? Right?
Right.
Big question. So let's take that up in the next segment.